Okay, this is chapter 10 still. This is section 10-2. This is recording number 2. All right, so we got to figure out how we're going to do this regression line, okay? So he's walking you through this, and this is so unfortunate that the notation is so weird, okay? And what he talks about here is that in a normal algebra context, in Math 35 or any algebra class you've ever taken, what we normally do is we say that the equation of a line is given as y equals mx plus b. M's the slope, b is the y-intercept. Now I can't review that for you because that's the subject of quite a few hours of discussion, okay? Hopefully you remember that or you've seen it before. You don't actually have to know all this to do this section, okay? Um, what he's saying here is you should study this before you look here. That's true if we were going to do the exercises, but I'm not going to ask you to do them. So I think you're okay if you're a little rusty on this, or if you've never seen it. All right. So unfortunately, in statistics, the equation is written differently. In statistics, they write it like this: it's y prime is equal to a plus bx. Don't ask me why. That's just the way they do it. Okay, so now a is the intercept, the y-intercept, and b is the slope of the line. And then they change the notation here to where instead of having x and y like they do in algebra, see this says algebra of a line, here it's the statistical notation for a regression line. So now it's x and then they call it y prime. That's a very, very bad notation. Okay, so moving forward, as you can see, and hopefully you're looking in your book, you've got the y prime intercept. Okay, so that's right here, y prime intercept right there, and then bx. The b stands for the slope. Okay, the slope is the rise over the run. So 2/4 in this particular case. So 2/4 is 0.5. So 5 is the y-intercept. 0.5 is the slope. Okay, so now there's several methods of doing this. Here's a couple of formulas they're going to give you. You're never going to have to use these. You just have to be aware of them. And they are right here. Okay, and what he's saying here is that you're going to use some of the same things that you computed before, you're going to use here. So what you do, if you were going to do this computation, is you would say, okay, I need A and I need B. Here's the formula for A, here's the formula for B. Okay? He's got a rounding rule, which we're not going to need to worry about. And then here's all these tables that he always has. So you can do this, but like I said before, you'd always just do it with a computer. Okay, so the equation of the regression line for the car rental company. Okay, so the you do all this. That gives you the A and the B. There it is. Okay, so there's the formula. If I were to say, what's the regression line formula, you would say, here it is. Okay, this is the slope. So what the slope does is it kind of predicts what's going to happen next. If you change x by a little tiny bit, you multiply it by the slope, 0.106 times that little tiny bit, that makes the y prime go up a little tiny bit. So this this 0.106, the slope, what it does is it predicts the future. It tells you what's going to happen next if you move x a tiny bit. That's kind of the intuition that you should have for that. Now, to graph a line, you select any 2 points for x and y, and I'm sorry, hold on one second. Okay, sorry. So you pick any two x values. Okay, so let's grab x equals 15, and let's grab x equals 40. So you plug in x equals 15 right there, and you do the calculation, and this is what you come up for the y prime. You take x equals 40, you plug that into this formula. The author is doing what I always say, and that is to write down the formula. So you write down the formula, you plug in x equals 40 right there, and what do you come up with? You come up with a y prime of this. So here's your y prime, here's your y prime. This y prime corresponds to x equals 15. This y prime corresponds to x equals 40. Then you plot those 2 points, okay? So we're going to plot those 2 points, and then you you draw a line that connects the 2 points. Now, why do you do that? Because 2 points determine a line. So once you have plotted those 2 points, then you have a unique line if you draw a line between them. And what I'm trying to do is find out where that's at here in the picture. Now, it's a little weird here because what he's saying is that uh, we've definitely got a point. X is equal to 15, y prime is equal to 1.986. So when we go here to 15, we should have a an actual point, and I'm not seeing it. Okay, so I'm not sure. I think this cartoon here really doesn't correspond that well to his example. Okay, and for sure, uh, x equals 40, y prime equals 4.636. That's not plotted here, okay? So I'm not sure what he's doing here. Maybe what he's saying is, well, I'm not going to actually draw those 2 points on here because then you get them confused with the data points. I'm going to just go ahead and, draw the line, and the only real points are the points that are the data points. These right here on this line, these are not real data points. These are merely my best prediction based on this least squares drawing, or this least square line that I have. I just don't know exactly what he's trying to do there, to be honest. Okay, so I'm going to come down here and we just talk about what's what's good about this. Why do we do this? Is the regression line value is that it can make predictions. Okay, and when you draw the regression line through the scatter plot, we should use these guidelines if we're going to make these predictions. We want the points of the scatter plot, the actual data points, to be a halfway decent fit. Okay, now that's in the eyes of the beholder. There are some statistical methods for doing the testing to see if it's really good or not. A little bit beyond the scope of this class. Okay, we want the value of R to be significant. It has to be where there really is this coefficient of regression that makes sense. Okay. The value of a specific x is not much beyond the observed values in the original data. In other words, you don't have ridiculous disagreement between the predicted version and the what we have in the original data. You don't want to go too far out. Okay, so like if you're like your data only goes out to right here. If you picked an X way out here, you know what? You're probably not going to be very, very accurate. Okay. So you got to be careful about things like that. Um, and then this is for the situation where if R is not significant, if you have a correlation of coefficient, but it's not significant, if it doesn't pass the hypothesis testing, then the only thing you can do, the best that you can do, the best predicted value for a specific x value is the mean of the y value in the original data. Okay, so this last one is hard to explain. The language kind of gets in our way here. So let me read it over, and then we'll go back to one of our cartoons from before, and I think we'll have a better understanding. So if R is not significant, that means that there's no real correlation. They just kind of bounce around. Then the best predicted value for a specific X value. So if you give me an X and I want to say, well, what's your best guess as to what the Y value is going to be for that specific X? Well, then the best you can do is just take the mean of all of the Y values that you had in the original data. So let's get a cartoon. It'll help us understand that. Okay, so this cartoon is from section 10-1. This is figure 10-1. Just by coincidence, it's the same number. So here we have an R value that's close to zero. There's no relationship. Okay, I want to be able to predict what the Y value is for some specific X value. Well, what I have to do is I just say to myself, well, I don't know what it is. I don't have a line that I can use to predict. So what I'm going to do is I'm going to just take the nearest Y values that I can and just say, well, it's going to just be the mean of those two guys, these two Y values. I believe that's what he's trying to say there. Not very clear, but I think that's what he's saying. Okay, so let's move on here. And we obviously we have a rounding rule. I think I mentioned that before. Now let me go back. It's so hard to bounce back and forth. So I'm going to just ask you to remember. Remember, I had the picture where I had the data points just kind of all spread out. I think another thing he might be saying here is he might be saying, listen, if you can't really give me your best estimate for what, let me go back to that. Okay, so here's the situation. R is not significant. R is, like closer to 0. Okay, so now I want my best estimate for a particular X. So here's an X right here. What's my best estimate? Well, what I'm going to do is I'm going to take, it's not good, it's not a good estimate, but the best I can do is to take all of these Y values here and say, well, the best guess I can get as to what the Y value is for this specific X guy, for this X, the best I can do is take the mean of all of these Y values, and that's as good as I can get. Okay, so the average of all the Y values, all these Y values here, the average of those Y values is the best I can do for some X value to predict what that X value is going to have as its Y value counterpart. I hope that makes it clear. Okay, so here's an example of where we're going to use this. We're going to talk about the absences in the final grade, that set of information there. So this is example 1011 here. Okay, so the equation that we came up with in example 1010, that was the absences in the final grade. Here's the equation that we came up with. Okay, that's our regression line equation. So now you can plug in anything you want. Like if the kid missed 4 classes, you plug that in, and this is your estimate of what the kid did. This is your estimate of the final grade if he missed 4 classes. Okay, so there's an example of estimation. Now, this may not sound very exciting to you, but believe me, this is just a metaphor. This concept, this regression type concept, is used all the time in science and engineering because you cannot possibly have all the data that you would like to have. So I'll just give you an example without giving you any classified information whatsoever. But one of the jobs that I had when I was in the defense industry was I ran programs, computer programs that calculated what are called signatures of space vehicles. Okay, and this you would create a model, a mathematical model of the space vehicle, and you would calculate all the sun and all kinds of inputs into that, generate a mathematical model of the heat, or more precisely, what the temperature was of the space vehicle. Then you could calculate what's called the infrared signature. Okay, so I'm going into down in the weeds here, but I got to explain what that is. So you would generate certain data points. You would generate whatever you're interested in. You could not possibly generate every single data point that you were interested in. So you would generate enough to where you would be able to draw a regression. We call it a regression curve. It may not be a straight line. It would be a curve, but the concept is still the same. So you would generate this curve, and then you would be able to do the calculations that you were interested in. So it's very, very useful. These are just metaphors. Don't blow it off just because these aren't very interesting, okay? All right. All right, I'm going to let you read all this part up here. I think it's pretty clear. Extrapolation, there's 2 concepts. There's extrapolation and there's interpolation. I don't think he has a cartoon here. Let's see if I can find one that works. Extrapolation is where you only have data that goes to 15. But let's say you wanted to you came down here and you said, oh, well, I want to know what it is for 20 absences. I don't have any data for that, not even close. If I plug it into the formula, that's called extrapolation, even though it's really not very scientifically valid. Interpolation is a completely different concept. You can Google that. We're not going to discuss it in class, but interpolation is where you go from this data point to this data point. You just draw a line from here to here. You draw a line from here to here, a line from here to here. So you have a whole bunch of lines that you're drawing, and then you are interpolating between the data points, is what we say. Okay, that's the end of this section, and that's all we're going to cover in chapter 10. Make sure you read the book. Okay, thank you so much.